Hello guys, let's have a look at this question. So this question comes under the topic of rotational mechanics. So here we have an object of a certain mass m as shown in the diagram. So this is point B unmarked. Let me mark the same. So here part A asks us compute the torque produced by the weight of an object when the line PC makes an angle theta with the vertical. Take counterclockwise as positive, and obviously if counterclockwise is positive, then clockwise will be negative. Now, I know that for part A, we get to calculate torque as torque tau is equal to the acting force F multiplied by the perpendicular distance D. If there is an angle between the force and the perpendicular distance, we know the angle also in the equation. Now, here the force acting is nothing but the weight W, which is given by mg. And if I were to draw a line like this, let me draw it better. A line like this and an imaginary line here, I notice that the perpendicular distance between the point of application of the weight or the force and the axis of rotation, this distance can be found out through basic trigonometry. I will use sine theta since sine is opposite over hypotenuse. The opposite side will become sine theta into the hypotenuse. So this distance will become d sine theta, giving my final equation for torque as torque tau equals negative weight, that is mg, into d sine theta. The reason I am writing negative sign is because the torque applied is going to be clockwise as shown here. And since they've asked counterclockwise to be positive, clockwise will be negative. Going to part B, they've said that theta is very small. When theta is very small, if you can remember this from calculus, just remember this. Limit theta tends to 0, sine theta over theta is equal to 1, which just tells me that sine of theta will be equal to theta approximately for very small values of theta. So doing the substitutions, I get torque as minus mgd theta instead of mgd sine theta. Now, they say that torque is minus k theta. Here I get the constant k as minus mgd. So this part is done. Moving on to the remaining part of the question, they say I have to bring equations to the form d square z by dt square is equivalent to minus bz, and use that value of b to find the time period. Now, I know that torque tau equals I alpha, and alpha is angular acceleration, which is double differentiation of angular displacement. If you want to go back to linear mechanics, just remember linear acceleration A is double differentiation of displacement or linear displacement. So angular acceleration alpha is just double differentiation of angular displacement d square theta, by dt square. So substituting that, I get tau equals I alpha, which is I into d square theta by dt square is equal to minus mgd theta. Bringing it to the form required here, I get d square theta by dt square is nothing but minus mgd divided by moment of inertia I times theta. If you notice, both the equations are in the exact same form, where z or z is replaced by theta and b is replaced by mgd by I. I will substitute the same here, giving my equation for time period t as 2 pi divided by square root of this b, that is mgd by I. That gives me my equation as 2 pi into square root of I divided by mgd. Now, again, this is time period T, we found out. So this was part C, I would say. Now moving on to the last part, that is part D. We notice here that assuming it were a uniform bar of mass m and length L, solve the or simplify the equations. With a uniform bar of mass m and length L, center of mass is going to be exactly at the center. So D is going to be L over 2. And as stated here, I is going to be over or equal to, sorry, 1 by 3 m L square. Just make the following substitutions. So my equation for T becomes equal to 2 pi whole under the root 1 by 3 ml square divided by mg. Now, D is L by 2, which I will write promptly as such. So L square and L cancels, M and M cancels, giving my final equation as 2 pi whole under the root 2 by 3 L divided by G. That's it. So this is the solution to the given question.